Let's recap exponential equations. So we want to solve this. 5 to the power of x is equal to 125. Well, this one's not too bad because it'll work out nicely. 5 to the power of what is 125? We know x is equal to 3. Terrific. 4 to the power of 2x plus 1 is 1 on 2 root 2. However, we can still do it by changing the 4 to 2 squared. And then on the right hand side we've got 2 to the power of minus 3 on 2. And so from there we can say, well, 4x plus 2 must have been minus 3 on 2. The powers must be the same. And we get x equals minus 7 on 8. But then we get something like this. 7 to the power of x is 32. 7 to the power of what is 32? Oh, no idea. So that's where we change it into a log. So we're now saying x equals the log of 32 base 7. Well, okay, it's an answer. But how on earth do I do that on my calculator? Well, we can't. Because our calculator only has 2 types of bases on it. It has base 10 and the natural logarithm. So the one that you might have thought was the in button is actually ln, and that's for natural logarithm. Ln, natural logarithm, shouldn't it be NL? No, because it's from the French, and French speak funny. They say words backwards. So they won't say natural logarithm, they'd say logarithm naturel. So all right, there's our formula. If we want to change it to a base that we can use, then it's still the log of what we're trying to find. So I've changed the base on the top, but I have to divide by the log of the old base. And then we can do it. So this one here, log of 32 divided by the log of 7. It does not matter which log button you use, just make sure you use the same one. And it should work. So 1.781. So that's telling me then that 7 to the power of 1.781, approximately, will give me 32. Oh, then something like this. 3 to the power of x is equal to 5 to the power of x minus 2. They're totally different bases, and I can't rewrite 3 as 5 to the power of something, or 5 as 3 to the power of something. So I'll just log both of them. So log both sides. We get the log of 3 to the power of x is the log of 5 to the power of x minus 2. Why do that? Because now we can use our rule that says the powers we can bring to the front of the log. And that gets the x out of the log. And just like any equation now, I just have to make x the subject of the formula. Okay, bit of playing around. We'll group the x's together. So I've got log 3 minus log 5. On the right hand side we get minus 2 log 5. So divide by, and notice I've swapped them round so I could get rid of that negative. So I've divided by log 5 minus on log 3. And then I can go to my calculator and work that one out. This one here, it actually is a quadratic equation. Now you might not see it straight away, but look at this. If I imagined m was 3 to the power of x, then m squared, I wouldn't write this down by the way, but I'm just letting you know what the thought process is. M squared is 3 to the power of x squared. Then using my index laws, I can say that's 3 to the power of 2x. But then reversing the order of those numbers then, that's the same as 3 squared to the power of x, which is 9 to the power of x. So in fact, we have a quadratic. That 9 to the power of x, if you like, is m squared, and that 3 to the power of x is m. I mean, some people even like to do a substitution to make it obvious. So there it is. M squared minus 4m plus 3. Let's solve that. And we get 2 possibilities. M is 3 or m is 1. Now, if you do it that way, don't forget to substitute back in, because the question wasn't what is m? The question is what is x? So let's sub back in, and we get 3 to the power of x is 3. Oh, that's nice and easy. X must be 1. And 3 to the power of x is 1. X must be 0. Anything to the power of 0 is 1. So we get x equals 1 or x equals 0. In equations, let's look at how in equations with, and this looks like a fancy heading here, continually increasing or decreasing functions. What is he talking about now? So, when a function is applied to an inequation, the inequality sign is maintained if the function is continually increasing. It's reversed if the function is continually decreasing. So this takes inequations a step further. Before, all we worried about was if we multiplied or divide by a negative number or something like that. But just like any equation, you can apply any function you like to both sides of the equation. But what do you do with the inequality sign? And it's all to do with the function that you're applying. If the function is continually increasing, then the sign's okay. If the function's continually decreasing, then you change the sign. If it's neither, then you can't use that function. So for something like this, I want to solve 1 is less than 2 to the power of x is less than 32. So as I say, both the exponential and the log are continually increasing curves. So I could apply either of those functions to this equation and the inequality sign will stay the same. Well, looking at it, it would be silly to do the exponential one. It's already an exponential. But if I log each of them, then it's still okay. And notice I've chosen base 2. And the reason I chose base 2, 2 to the power of x. That's how I will undo the 2 to the power. Keep the base the same. So let's look at our equation now. Log of 1 base 2. 2 to the power of what is 1? 0. Let's have a look at the right hand side. Log 32 base 2. 2 to the power of what is 32? Hang on, what is it?
5.
It's 5. Okay, I'll take you at 5. And the middle one just becomes x. Bang, we've solved it. X is in between 0 and 5. Let's try a second one here. So the log of x base 3 is greater than 2. But this time I'm going to use the exponential because it's also a continually increasing curve. So 3 to the power of log x base 3 is greater than 3 squared. But one of our rules says if we have a base to the power of log of that base, they will cancel each other out. And so in this case, I'll just be left with x. X is greater than 3 squared. X is greater than 9. We shall do 8e.